From an earlier discussion of Ohm's law, we mentioned that there is a predictable relationship between voltage, current, and resistance. This relationship is somewhat altered when we deal with AC current flowing through circuits that have inductive loads, such as motors or solenoid coils. The changing voltage in an AC circuit leads to changes in the strength of the magnetic field as a result of Ohm's law. These changes in the magnetic field produce a second voltage called induced voltage, which counteracts the effects of the original supply voltage. The supply voltage must first overcome this induced voltage before current can flow. This effect, called inductance, causes a voltage to lead the current because voltage is applied before current can flow in the circuit. In addition, alternating circuits are also affected by the opposition created by the changing of direction of current flow in an AC circuit. This resistance is called inductive reactance. Inductive reactance also causes the voltage to lead the current in AC circuits. In addition to induced voltage, capacitors also have an effect on the relationship between current flow and voltage in AC circuits. Capacitors are designed to store electrons and are commonly found in the circuits that control the operation of electric motors. Capacitors charge and discharge at the same rate as the voltage applied to the circuit. When the supply voltage and the capacitor charge reach zero, there is no opposition to current flow, and the current is therefore at its maximum. This causes the current to lead the voltage. This interaction between current flow and applied voltage is called capacitive reactance. The sum of the circuit resistance, inductive reactance, and the capacitive reactance is called the circuit impedance. Reactance has an effect on the power of the circuit because the voltage and current are not working together. The actual circuit power will be somewhat less than the calculated power. In a circuit with no reactance, the actual power will be equal to the voltage multiplied by the circuit current. If the voltage is 100 volts and the current is 10 amps, the power will be 1,000 watts. However, if there is reactance in the circuit, the actual measured power may be only 900 watts. The ratio of the measured power to the calculated power is called the power factor. Using our previous example, the power factor can be calculated by dividing the measured power of 900 watts by the calculated power of 1,000 watts, given a power factor of 0.9. The closer the power factor is to 1, the more efficiently power is being utilized in the circuit.